Hi everybody, welcome to section 9.5, which is on the z-test for one proportion. This test compares the population proportion to a constant. So just like when we've been doing the tests for the mean, where we're comparing the mean to a given value, this is just like that, except it's for the proportion. Just to remind you of a little bit of notation, P, just P by itself, represents the population proportion. This is the thing we're trying to generalize about or infer to. A P with a bar over it, P bar, is the sample proportion, which is our best estimate, our point estimate for the population proportion. And these are the two things that are going to be the most important for us today. But don't get those confused with the p-value, which is still the probability of making a type 1 error. This is the thing that we are comparing to alpha, so that we can determine whether or not to reject the null hypothesis. So just like before, there are three possible sets of hypotheses for this test. P naught is the hypothesized value, and this will always be a value between 0 and 1 because, you know, proportions always have to be between 0 and 1 or 0 and 100%, same thing. So for all of these, our null hypothesis can be written as P equals P naught. Your book will write these as inequalities, but you don't have to do that. You can just write them as equalities. Because I think that makes it easier, but whichever way you want to do it is okay. The alternative hypothesis could be that P is less than the hypothesized value. It could be that P is greater than the hypothesized value, or it could be that P differs from the hypothesized value. And here's our test statistic. This formula comes from, just like we had a sampling distribution for the mean, there's one for the proportion. And that is used to construct this test statistic. You don't have to know, the details of where that comes from, but I do want you to be aware that that this comes from a sampling distribution. The p-values, if you notice, this says z here. That means this is a z-test, which means to find the p-values, you're going to use the normal distribution. So norm S dist. So these formulas are exactly the same. In fact, I just copied and pasted from the z-test lecture. All right? So we are not going to, set up these every time. We're going to do a template just like we did before, because that's going to help us with our efficiency and that's going to help us with our accuracy. Both of which are good things. So let's come over here. You may want to keep all your templates in one file. I think that might be a good idea. All right, let's leave a column over here because we may want to use some data a little bit later on, and we want to leave a column for that. So some things we're going to need. We're going to need the hypothesized value for P. We are going to need X. We are going to need N. And I guess that's it. So I'm just going to make something up here so we have something to type in. So let's suppose our hypothesized value is 0.5. And then X is 79 and N is 183. So we first need our test statistic, or actually we should probably do our p-bar. Okay, so our sample proportion. So our sample proportion is going to be X divided by n. So we get, in this case, 0.43169. So now we need our test statistic. And if you prefer to split this up, because I know this is a little bit of a complicated computation with with parentheses in the denominator. If you prefer breaking that up into a couple of steps, that's fine. But I'm not going to. So on the top, we're going to have P bar minus our hypothesized value. And on the bottom, we're going to have the square root of this whole term. Okay. And inside that, we're going to have a numerator and a denominator. And in the denominator, we've got n. Okay. Now, I've done these parentheses where we make sure we include the n inside the square root. Okay, so that'll give you an error if you don't. So be careful with your parentheses. So inside this parentheses, we've got our numerator, which is going to be P naught. So our hypothesized value for P times 1 minus our hypothesized value. Okay. And it may help to count the parentheses. So we know we've got this one closed, but on the top or on the bottom, we've got 1, 2, 3 open ones and 1, 2, 3 closed ones. So that's a good sign. So we get our test statistic of negative 1.8481. And then we're going to need our 3 possible p-values. So we've got our p-value if the alternative hypothesis is p less than p naught. And I just realized I maybe should not have just copied that over without changing these mu's to p. So I told you I copied them right over. But that's the only thing that changes. And then we're going to have the same thing but one for greater than and one for not equal to. So for the less than case, it's just norm as dist. The value we got for our test statistic, comma, true. For the greater than case, it's 1 minus the same thing, norm s dist, z test, comma, true. I'm going fast, but you can pause it if you need to. And our p-value here is going to be 2 times parentheses 1 minus norm s dist, and then we take the absolute value of our test statistic, close that, and type true. And let's count parentheses just to be sure. We've got 1, 2, 3 open, but only 2 closed. So that means we have a problem. So let's see where we have our problem. So you're getting a little bit of practice on troubleshooting here. We know we're good on our absolute value. So you always start from the inside out. So we've got this one closed. How about the normal distribution? Well, we've got that one closed. We're good on that. But now we need another one to close the 2 times quantity. All right. So we've got our 3 p-values, and we are good to go. So let's do an example. Suppose we're taking a sample of 300 women, and we find that 228 of them have ever dyed their hair. So let's test whether more than 75% of all women have ever dyed their hair. So let's set up our hypotheses. That's too broad of a tip. No. So our null hypothesis is going to be that P, and this has to be P and not mu now because we're doing with the proportion, equals 0.75. And the alternative hypothesis, HA or H1, doesn't matter which, is going to be greater than because that's more than. So based on this information, we're taking a sample of 300 women, so N is 300. And we find that 228 of them have ever dyed their hair, so that means X is going to be 228. And our test value is 0.75 because this is what we want to test. So let's go over to our template. And our hypothesized value is 0.75. Our X was 228. And our N was 300 in this problem. So our sample proportion is 0.76. This was our test statistic. And so let's go ahead and write down what our test statistic was. So Z star was equal to exactly 0.4. And our p-value, we are picking the greater than one because our alternative hypothesis was greater than. So we're looking for this one here, so 0.3446. They specified in the problem to use alpha equals 0.05. So we're going to reject H naught if the p-value is less than 0.05. And I do need you to state that every time. Okay. I'm letting you off the hook doing these tests using the critical value, using something called the critical value approach, which is using the test statistic instead of the p-value. But show me every time that you remember this. So our p-value is not less than 0.05. Therefore, we are going to fail to reject H naught. And say that there is not sufficient evidence to conclude that P is greater than 0.75 In other words, we cannot conclude that more than 75% of all women have ever dyed their hair. Okay, moving on to our next example. Here's a data set on people's uses of mobile devices. So we've got the primary device that the device that they use the most often, whether that's a phone, a tablet, or a laptop, and then some other information as well. But we're going to use this variable. So I'm just going to copy this over into our template. And the question is, based on this information, can we say that more than a third of the people in the population use a tablet as their primary electronic device? So we put our data over here, just pasting. And here in, it's easy to go and just count. We've got 86 rows of data, but the first one was a title, so 85 is our N. For our X, let's use the COUNTIF function. And if you forget how to use that, you can just, type in COUNTIF and then click the FX. The range is all of that entire column. And the criteria is we want to know how many of them said tablet. So we have to put quotes, tablet. And click OK. This tells us that 39 people said tablet. Our hypothesized value is 1/3. So we'll do equals 1 divided by 3. And now we have our test statistic, we have our p-value, and we are good to go. So setting up our hypotheses, we've got the null is that p equals 1/3. And we're going to leave that as 1/3. Please don't round that to just 0.33 because that's not the same as 1/3. And we've got our alternative hypothesis is that p is more than 1/3. And from our template, we've got that z star is 2.4543. So 2.5453. And our p-value is, we're picking the greater than one. So 0.0071. And it was just a coincidence that both of these examples were greater than. You could have any one of these on in your homework. So 0.0071. So we're going to reject H0 if the p-value is less than. Now in this problem they didn't give you a value for alpha. Anytime they don't, you can assume 0.05 if you want to. But notice here that it really doesn't matter which one of the three common values we're using. Even for the smallest one, we'd still reject H0. So if we said just 0.01 here, we'd still get the same conclusion. Okay, so we'll just pick the smallest one because that's the strictest one anyway. All right, so we know here that this p-value is less than 0.01, so we're going to reject H0. And say that this is sufficient evidence to conclude that P is greater than 1/3. So even if you can't see that, you know that's what I'm writing, because my mouse pen is cranky today. All right, so that's it for this lesson, and please let me know what questions you have. I'm always happy to entertain questions.